Hello, everyone. My name is Meritxell Riera-Marin, and I'm going to be presenting this work called Multi-Rater Calibration Error Estimation. So, our work focuses on building trustworthy AI, where calibration is a key pillar. And what is calibration? Calibration is the reliability of predicted probabilities and how they match the actual ground truth. It can take many forms, and it is not a binary property. It can go from underconfident but accurate to overconfident and wrong, and anywhere in between. So it is important for medical AI because poor calibration might lead to over or underconfident models, which is critical for decision making, for example, when diagnosing tumors, malignant or benign. So in this work, we address two key challenges. First, in medical imaging, expert annotations frequently disagree due to ambiguity in cases such as tumor boundaries or lesion diagnosis, introducing variability into the ground truth. And second, calibration error estimates tend to be really hard to measure and stable when used with small test sets. So the question is, instead of treating rater disagreement as a noise and usually merging the different annotations into one, could we actually leverage the presence of multiple annotations to improve the stability of the calibration error estimates? So this is the mathematical definition of the expected calibration error. And our proposal is to extend the definition of the calibration bin so they can actually accommodate multiple equally valid labels, for example. In medical images, as already said, the annotators may provide different ground truths for the same case. So instead of merging them into one, which we will be actually losing valuable information about disagreement, we treat each annotation separately. So this means that even if a model outputs the same confidence for a sample, each annotator's level is considered independently within the same bin. So as a result, the bin contains richer and more information about the distribution of the possible outcomes, which allows us to compute a more informative and robust estimate of the accuracy. So there are alternative ways of estimating calibration error, which replace, for example, histograms and binnings with kernel density estimates. In our study, we also compute kernel density estimate calibration error to benchmark our proposed CE and study whether our proposal is orthogonal to the base calibration error being used. So our goal is to obtain calibration error estimates that are as stable and robust as possible. To evaluate this, we measure the stability of calibration error estimates under limited test data by computing their total variation as the test sample decreases. On the plot in the right of the slide, you can see both EC and kdeECE compared with their respective multiple rater versions. The x-axis shows the percentage of the test data being used for the computation, while the x-axis shows the calibration error. You can see how the standard versions show more jumps and instability as the test size decreases, and the multi-rater variants are much smoother. To quantify this behavior, we will be using the total variation equation in the left of the slide. And we will be evaluating our approach on several datasets, covering both classification and segmentation. For segmentation, the problem can be seen as a pixel-wise classification, so everything we described can be applied as well. And for reporting, we compute one calibration error per image and then take the average across the dataset. So in the numerical results, we can see that both multi-rater variants clearly show reduced variability and greater stability, where the standard estimates tend to have a more variation. For the dispersion measures, we used bootstrapping by resampling the test set 100 times, which allowed us to actually assess how consistent the calibration estimates remain across different subsets. So as conclusions, we can say that virtually we expand the data set of the amount of the size of the test set. It shows greater reliability on the CE estimates and greater robustness as the test size decreases. And it is orthogonal to the improvement of the adopted base CE estimates. And as a future work, we will be exploring new stability metrics for the CE estimates beyond total variation, and also training methods that enhance calibration using multiple label annotations. Thank you very much.